Here's another example of an optimization problem. This one says determine the point in the parabola y equals x squared minus 25 that is closest to 0, negative 3. So a little bit different, not really a word problem. But like all questions, let's create a diagram here to start this off. Okay. We know this parabola x squared minus 25 is just going to be the x squared parabola brought down 25. So it should look like this. And closest to 0, negative 3. So x value 0, this value negative 3. Okay? So we're going to need to find what point on this parabola here is closest to the point 0, 3. I'm going to give it an AB value. This AB can be any point along this parabola, and we're going to use this to figure out what's closest to 0, negative 3. Note that it is a parabola, so we will have two answers, because if AB here is close to negative 3, then negative AB is going to be the same distance. And distance is what we're looking for. So you need to know that distance formula, where you have d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. This is a formula that should just be in the back of your pocket. When you see something that's closest, it should indicate you want to minimize distance. Okay? That's pretty straightforward. If you're close to something or how you get closest to something is going to be the minimum amount of distance between that thing and yourself. So, we're going to use this distance formula, and we're going to plug in 0, negative 3, and AB. Okay? So we're going to have d equals x2, let's make this the square root of a minus 0 squared plus b minus negative 3, so b plus 3 squared. Okay? And we want to have this d be a function of one of these variables. So it's a squared and then b plus 3 squared. Now we have another equation here, and since AB is on our parabola, then we can plug AB in for y and x, such that b equals a squared minus 25. And we can plug that value in for our b value, and expand this equation from there. So d, as a function of a, equals the square root of a squared plus a squared minus 25 plus 3, so a squared minus 22 squared. Okay. Let me expand what's in this bracket here. We're going to have d as a function of a. I'm going to expand this before I take the derivative because it will make it a much easier derivative. The square root here of a squared plus a to the 4 minus 22, so 44a squared plus 22 squared. Okay? And that value there, we can take the derivative of. D prime of a is going to give, because this is 1/2, so we're going to have the derivative of the inside over top here. I'm going to change a squared minus 44a to just be negative 43. So the derivative of this is going to be 4a cubed minus 43 times 2, so 86 minus 86a. This 22 squared will be gone, all over 2 times the square root and what we had in here, so a to the 4 minus 43a squared plus 22 squared. Whew, big derivative. You notice I'm not evaluating 22 squared because I know that when I set it equal to 0, it's just going to go away. We set this equation equal to 0, we're going to have everything on the denominator go away. So we're going to have 0 equals 4a cubed minus 86a. Bring that over to the other side, and we have 86a equals 4a cubed, meaning this 86 over 4 equals a squared, and the square root of 43 over 2 is a. Square root of 43 over 2 is a. That's our value that's going to be, that's our x value that's going to be closest to 0, -3. Because we took the square root here, you do have to have plus minus, because for 43 over 2, this a is going to be as close as the -43 over 2 is there. Okay, we can plug that back into any of our equations to find our b value. This one's going to be easiest, because a here plugging in is going to be 43 squared, square root over 2. That's going to cancel out. So b equals 43 over 2 squared minus 25. b is going to be 43 over 2 minus 50 over 2. So b is -7 over 2. And we now see that the point closest to 0, -3 is plus minus the square root of 43 over 2, -7 over 2. And that's a second example of optimization problem.